Hello everyone. In the last session, we looked into truss elements or the bar elements which are inclined to the x-axis by a certain angle, and then we formed a generalized stiffness matrix and we did a numerical on one of the truss elements where you obtained the displacements under the given loading condition. Now today we are going to look into beam elements. Beam elements are the flexure elements. Now the difference between the bar element and the beam element is that the beam elements will undergo rotation as well. So if you have a beam element like this, let this be your node A, this be your node B, then each of these nodes will have 2 degrees of freedom. This is your first degree of freedom, this is your second degree of freedom, and here also you'll have 2 degrees of freedom, but let's label this as 3 and this as 4. Now your boundary conditions or loading conditions will occur at these nodes, which means that your forces and displacements will occur in these degrees of freedoms. Let these be u1 and f1. This will be u2 and f2, but you can write here theta 1 or m1 for rotation and moments, because rotation and moment will occur here, but in this case I'll just be writing u2 and f2, and for this one you'll have u3 and f3, and here you'll have u4 and f4, or you can write here theta 2 m2, and you can replace this one by u2 or f2 as per your convenience. But here I'll be writing u4 f4, u3 f3, u2 f2, and u1 f1. Now please be careful, because our solution will be based on this configuration where we have taken upward degree of freedom as positive and anti-clockwise rotation as positive. So this is our positive sign convention. Now here what we have to do is we have to find the stiffness matrix for the beam element, as it will link all these degrees of freedom together. So here what we have to find is we have to find forces which will be developed by applying a unit displacement in these degrees of freedoms. For example, if we apply a unit displacement at u1, then we have to find what will be the force at f1, what will be the force at each of these degrees of freedoms. Similarly, here also you have to find, when u2 equals to 1, you have to find the forces in each of the degrees of freedom. All this will give you your stiffness matrix. We can also write, because we are looking the effect of degree of freedom 2 on degree of freedom 1. Here degree of freedom 2 on degree of freedom 2, and so on. Now to do this, we have to apply unit displacement in each of these degrees of freedom. Let's write here case 1, where we displace end A upwards by a magnitude of u1 that equals to 1, and we have to keep other boundary conditions fixed. So you can see here that when you have a beam like this, This is our end A, this is our end B. So you'll be displacing our end A upwards, that is in degree of freedom 1, by u1, which equals to 1, and you'll be keeping other degrees of freedom fixed. Now what we'll have here is your beam will deform like this. Where this will be, and this will be your final position of the beam. Now because of this, there will be two forces developed, which will be P and your moment here. Therefore, what you have to do is you have to separate this by applying superposition theorem, where you separate the beam into two parts like this, plus like this. You'll have your P applied here and your moment applied here. We're going to apply moment area theorem to obtain the forces. Your moment area theorem defines that the total area under the M by EI diagram will give you the change in slope between the two ends considered. Now when this change is multiplied by the centroid of the area, then you'll obtain the relative displacement. If you have a beam like this, let's take this one here, and let's say this beam has a length L and its elastic modulus is E and moment of inertia is I. What you'll get is you'll have your beam like this and you'll have force applied like this. Now this beam is going to deflect like this under the force. Now you'll see that this region here is the tension region and this region here is the compression region. Now I generally plot our moment diagram in the tension region, so therefore our bending moment diagram will be something like this in positive sense, and this value here will be PL as a moment, and you can divide this by EI to obtain the M by EI diagram. For these kinds of beams, these are the prismatic beams where the cross-sectional area is same throughout the length. Therefore, your EI is constant throughout the length. Otherwise, if you have a beam that is like this, then you can see that your cross-sectional area is varying. Therefore, your EI will also be varying. And you'll see that your EI will be a function of x, not a constant. Therefore, your bending moment diagram may change. Now for the other case, you have a constant moment applied. So you take that beam out. And here you'll see that this is in anti-clockwise direction. And because of this, your beam is going to bend like this. Now here, the tension region is this one and the compression region is this one, and we plot our bending moment diagram in the tension region. Now your bending moment diagram will be a constant because you have a constant load applied. Now this value will equal to M. This will be equal to m by EI. Now we have our bending moment diagrams for the two cases, and the centroid of this diagram is at 2/3 of L when this is L, and the centroid here will be L by 2 from here when the total length is L. Now if we apply our moment area theorem, then our change in slope between this is A, this is B, this is A, this is B. Now you'll see here that your theta at A, due to your applied load P, will be equal to the area of this triangle, this bending moment diagram, which will be half PL by EI times L. That will be PL squared by 2EI. And also your delta at A due to P will be your area times your centroid. Your centroid is 2y3 times L. Now this will be equal to PL cubed by 3EI in the upward direction. For the moment case, your theta when moment is applied at A will be given by your area. Your area is M by EI times L, so ML by EI, and then you will have your delta displacement due to moment at A will be given by your area times your centroid. Your centroid is L by 2, so this will be equal to ML squared by 2EI. This one will be downwards. This will cause this one to rotate in this direction and this one to rotate in this direction. So you can say this one is anti-clockwise and this one is clockwise. Now this is our displacements at A due to the moment and due to the load. Now if you look at the boundary conditions of our beam, you'll see that here the total displacement is u1 equals to 1, but you'll see that the rotation here is 0 because we are locking all these degrees of freedoms. Therefore, in this case, your rotation, which is due to P and M, should be equals to 0. Now what this will give you will be PL square by 2EI minus, which is clockwise, plus ML by EI equals to 0. Now this will give you a relation between your moment and force where M equals to PL by 2. That's the equation number 1. And then you'll see that the total displacement due to P and due to M at A must be equal to U1. Now this will give you PL cubed by 3EI minus ML squared by 2EI equals to U1. Now when you substitute your M here and you solve it, you will get the value of P. Your value of P will be 12 EI by L cubed times U1. You can keep U1 as it is, or you can replace that by 1. I'll just keep it as it is. So that's your force. Now for your moment M, you substitute this value back here. Now you'll get 6 EI by L square U1. So that's your moment. So from these cases, you'll see that your P corresponds to your F1 and your M corresponds to F2. Therefore, now this gives the effect of your U1 on F1 and F2. Now when you apply your equilibrium equation, or you can take a moment at this point, let's take a moment here. Now what will happen here is you will get F1 times, if the length is L, times L, which is clockwise, let's make it negative, and then you have plus F2 and then plus F4 equals to 0 when you are taking a moment here. Or we know F1, we know F2, now you have to find F4. So F4 will be 6EI by L square. So now we have our F4 as well, but F3 will be equal to minus F1 in the equilibrium case. This will be equal to minus 12EI by L cube U1 U1. So in this figure, what you get is when you apply a displacement U1 in this direction, what you'll get is you'll have your force F1 as 12EI by L cube U1, and you'll have your moment as 6EI by L square U1, and here F3 is in negative direction to F1, which is this. This will be equal to minus 6EI by L square U1, and you have your moment as 6EI by L square. Sorry, this is 12EI by L cube U1. So you can see here that we have formed a relation which links the forces obtained in the degrees of freedom with the displacement occurring in 1. Displacement or the motion in 1 degree of freedom can cause the effect on each of the other degrees of freedom. Now this is our case 1. So for case 1, we have obtained all our forces. Let's look into case number 2. In case 2, what we're going to do is we're going to rotate end A with an angle of U2 in the positive direction, which is this direction, and we're going to keep the other degrees of freedoms fixed so we can obtain the reaction forces. So for this case, what we'll have is a beam like this, right? Now what we're going to do is your U2 is this direction, so we're going to apply U2 in this point, so it will be something like this, and this won't be fixed because we are releasing this rotation, so it will be hinged now, so it will be like this. Now this is our U2. Now because of U2, there will be force F1, there will be force F2, there will be force F3 and F4. Now here also what we will do is we'll write this one as a superposition of two forces. Now this will be like this. We have P here, this is L, plus we'll have M here, and this is L, like this. So here also your theta, if this is A, this is B, A, B, theta A due to P will be equal to PL square by 2EI. They will be same as this one. And also, now in this case, you can see the boundary condition here that your delta here, or you can say your u1 equals to 0, which is this one, but your theta equals to u2. Now if you use superposition, then your rotation due to force P and rotation due to force M should be equal to u2, and your displacement due to P at A plus displacement due to M at A must be equal to 0. Now if you use this condition, what you will get is the relation between P and M, where M will be equal to 2 by 3 PL. And in this one, what you'll have is you'll have minus PL square by 2EI plus ML by EI equals to U2. And when you substitute your M back here, then what you'll get is you'll get your P as 6EI by L square U2, and then you'll obtain your M from here. It will be 4EI by L U2. Now this P corresponds to F1 and this one corresponds to F2. Now you can use your equilibrium equation to obtain F3, which will be equal to minus F1, which equals to minus 6EI by L square U2, and F4. For F4, what you do is you have to obtain your moment there, that equals to 0. So in the equilibrium case, it will be F1 times L negative, and then plus F2, and then plus F4 equals to 0. Now this implies 2EI by L U2. Now we have our F3 and F4 as well. So in this case, what you'll get is you'll have this, and when this one is rotating like this, you'll have your F1 here, which will be equal to 6EI by L square U2, and you'll have your M, which equals to F2 will be equal to 4EI by L U2, and here is 6EI by L square U2 in downward direction, and this one will be 2EI by L U2. So here we know the effect of U2, that is the second degree of freedom, into all the other degrees of freedom. Now similarly, you can do similar cases like for U3 equals to 1 or U3, it will look something like this, where you are applying U3 and you have to obtain your F3, your F4, F1 and F2 for this case, and you have to obtain your forces for this case as well. So this is your U4 in the positive sense. You got your F4, you have to get your F3, you have to get your F1, and you have to get your F2. So here you will know the effect of U3 on all the degrees of freedom, and you will get the effect of U4 in all degrees of freedom. Now when you do this, what you'll get is, I'll just write the solution here. You can now do this yourselves. So this will be your solution. Now you have to add these up. As explained before, you can write 3 here. You can write 4 here, because this is the effect of 4 on the other degrees of freedom. Your F1 will be equal to F11 plus F12 plus F13 plus F14. So if you write this one, your F11 will be 12 EI by L cube U1 plus 6 EI by L square U2 minus 12 EI by L cube U3 plus 6 EI by L square U4. Similarly, you can write it for F2, F3 and F4. And you can see here that all of these have U1, U2, U3 and U4. Now you just have to write them in the matrix form. You look at F1, F2, F3, F4, which will be equal to, you will have a big matrix here. It will be 1, 2, 3, 4, 1, 2, 3, 4, and here you'll have displacements U3, U4. Now here, this one will be, I can see here that this matrix here is symmetric. Now this is our required stiffness matrix for the beam element. So there we have it. If you have a beam like this, we're going to separate the beam into different elements by these nodes here, and we're going to apply this matrix for each of these elements to obtain the element level stiffness matrices, and then find a global matrix by summing them up as we did before. So this is how you obtain the stiffness matrix through moment area theorem. Let's look at a numerical example. We have a beam like this, which is a two span. Here and here we have rollers, and let's say we have 30 kilonewton load occurring here, and we have 20 kilonewton meter of VDL applied in this part. Let this be 3 meters, this be 8 meters, and this one be 6 meters. This is A, this is B. Now this question was asked in the examination of 2072 Aswin. Now the problem here is to find the deflection at the midspan of the given structure. So it is just asking us to find what is the deflection at this point here, which is only the rotation, and this is point C. Now E for the whole length of the beam is given as 20 into 10 to the power 5 MPa, and moment of inertia as 5 into 10 to the power 6 millimeter to the power 4. The first step here is to discretize the beam. We can discretize the beam into two parts. Now this will be our first element and this will be our second element. Now for the first element we have, and we have the other part. Now when doing this, what we have to do is we have to transform these into fixed boundary conditions. So what we'll have is, now we have to find our fixed and reactions. We have to form our stiffness matrix for each of these elements. Now if we draw a free body diagram for the whole element, this is A, this is C, this is B. Let's label this as 1. This will be 2. This will be 3. This will be 4. This will be 5. And this will be 6. Now we have separated this into two elements. We are to form our stiffness matrices for each of them. So for element number 1, your K1 will be equal to, and here you'll obtain your stiffness matrix. This is a symmetrical matrix. Now degrees of freedoms will be 1, 2, 3, 4, 1, 2, 3, and 4. Now let's look at another element, your element number 2. For this one, your K2 will be, here you'll have 3, 4, 5, 6. Here also 3, 4, 5, 6. This will be a symmetric matrix as well. So this is your K1, this is your K2. Now you have to form your global stiffness matrix depending upon the degrees of freedom. So your global stiffness matrix, let's write it here, Kg will be equal to, you'll have your EI as common in both of them. So for this one you write all of your degrees of freedom. Now for 1, 1 you have to look here, 1, 1, so this will be this value here, and for 1, 2 it will be 0.0938, 1, 3 it will be minus 0.0234, and for 1, 4 it will be 0.0938, and 5 and 6 we don't have it, so it will be 0 and 0. For the next one, let's start here. This 2, 2 will be 0.5, and then we have 2, 3 which will be equal to minus 0.0938, and 2, 4 will be equal to 0.25. We don't have 2, 5 and 2, 6, so it will be 0 and 0. Let's look at other one. Let's start from 3, 3. So for 3, 3 we have two values. We have this one and this one, because this is a common node between element 1 and element 2. So to add them up, then what you'll get is, if you add these two up, your 3, 3 will be 0.790, and your 3, 4, which is this one, and also this one, when you add that up you'll get, and 6, 6 is this one, 0.6667. Now this will also be a symmetric matrix. So I have to write an equilibrium equation now. Now for this case, if you look at the boundary conditions, you will see that U1, U2, U3 and U5 are 0. So in this case, and you have to find U4 and U6. Now for the loading case, you have to find what will be the forces at these ends. This will be F1, F2, F3, F4, F5 and F6. Now to do this, for the first element we have a 30 kilonewton load acting here, and for the second element we have 20 kilonewton per meter force acting. So for the first one we have F1 will be acting downwards, so it will be minus, which is opposite to this direction here. You can see here the loading here is anti-clockwise, so this is positive. Loading here is in clockwise, that's negative. They are acting downwards, so F1 and F3 will also be negative. Now for the second element, now you can see here that there are two F3s and two F4, because this is a common node. Therefore you have to add those values up. Your force vector will be equal to, now these forces are known as fixed and reactions. Now to find your global force, as you can see in your main structure, that you'll have a reaction force R1 occurring here, reaction force R2 occurring here, reaction force R3 occurring here, and then R5 occurring here. We also have to add these reactions to our forces. Your F1 will be plus R1 because we are taking this as positive for reaction, and F2 will be plus R2, F3 will be plus R3. For F4 we don't have any reaction force. For F5 we have plus R4, and for F6 we don't have any reaction force, so this one is R5. Now we have our global force vector as, therefore we only have to look into degree of freedom 4 and degree of freedom 6. So this is our 4, this is our 6. Now also in the stiffness matrix, the global one, we have to look into 4 and 6. So this is our 4 4, this is our 4 6, this is our 6 6, and there will be 6 4 here, which is symmetric, means that this value will be equal to 4 6, which will be 0.3333, which will be equal to this one. Now you can write your simplified equation below. Now we have to solve for U4 and U6. So this one is in kilonewton meter, this one also kilonewton meter, so I have to change that to Newton millimeter and Newton millimeter. So for this one you have to multiply this by 10 to the power 6, and here also 10 to the power 6. Now if you want to find your forces, then what you have to do is you have to substitute these values back here and then solve for your reactions, which are R1, R2, R3 and R5. You can separate your vector, this one, as you can take this one. Now you have all your values here, you have this one, you can take this one on this side and you can solve for your reactions. You can look at another problem in my another playlist, which is chapter 1 in abacus modeling 5. You look at beam modeling and you'll be able to see a numerical example there as well, and you'll also be able to visualize the solution that we obtained. So this is how we solve for beams using the beam element stiffness matrices. So you just have to be careful about your sign convention here. We generally take upward direction as positive and anti-clockwise direction for the moments or rotations as positive. This stiffness matrix is obtained by assuming the upward direction positive and anti-clockwise rotation as positive. So this is it for today. Today you learned about beam element and the procedure to obtain the stiffness matrix for the beam element, and we did a numerical where we solved for the displacements and reactions under the loaded condition. Thank you for watching till the end. Hope this was helpful. See you next time.